existing infrastructure available on the site, okay, and you wanted to equip that infrastructure with the Bess. And the infrastructure SLD would be something like this. There is existing, let's say, breaker systems, then existing transformer available, right? The main transformer. There is a breakers, right? This is HT breaker, this is ST transformer, okay? And here it is going to be converted on HT to LT. And then there is a LT panels and specified load. So this is, let's say, existing system, okay, with the architecture. Now, what is their rating that we will see? And even if there is a rating existing, after putting our new plant, what upgradation they needs to carry it out, okay, that we will refer in the entire journey. So you just remember the architect, the network, what the site is having right now, okay. So what is the requirement? A company wants to set up the power plant with the Bess, right, to meet their energy requirement. Overall, company will require 9.5 megawatt of a daytime load and 4.5 megawatt of a nighttime load. And what they are asking us, kindly suggest them the best size of solar power plant equipped with the battery energy storage system. When 80% of a daytime load should operate on the solar plant and 100% of a night load should operate on a Bess. Further, factory may go for further expansions of the plant. Also, maintain 1 day autonomy in the base to operate the night load. Selected battery capacity should be capable to fulfill the energy requirement until 10 years of its operation. What they have shared us, the very raw inputs and very basic inputs. And everywhere, if you are trying to approach a new plant, nobody will going to share you every detail. They are just sharing, I have a plant size of, let's say, 9.5 megawatt, or the load of 9.5 megawatt in the daytime. Nighttime load is 4.5 megawatt, correct? And I want to solarize my load, or the solarize my factory with 80% of its capacity in the daytime, and during the night I wanted to operate every load on a Bess. So kindly suggest us the battery capacity, kindly suggest us the solar power plant size, and consider the battery should have 1 day autonomy, right? Additionally. So even if we not able to get the charged batteries, then also battery should power my load for a 1 day, right? Another 1 day. And also lastly, they mentioned the plant should run with full of its capabilities for minimum 10 years. So it means whatever the units they required at the end of 10th year, right? Accordingly, we need to select the size and all. So what could be the first step we should have? First thing is we need to write down the given input.
Yes,
The first thing
is we can know the 9.5 megawatt. It is for how many hours?
Very good. So 9.5 megahertz is the constant load considered.
Constant from our let's say from 6 a.m. to 4 p.m. like that.
No, 6 a.m. to 6 p.m. you can consider.
6 a.m. to 6 p.m. Okay.
12 hours. 12 hours.
Around 12 hours. Yes.
Yes, yes. It's 12 hours day, 12 hours night. That's the consideration.
12 hours, and 80% is from the solar panels, and the other 20% is from the grid or from the batteries?
From the grid.
From the grid.
Not from the batteries.
You have 7.6 megawatt by 12 hours. Hello?
Hello?
Yes, so 7.6 by 12 hours.
Yes, if you look at the inputs, they are stated 9.5 megawatt for the daytime, right? Nighttime 4.5, battery backup 1 day. I'll reach to your point, okay? Solarization, they required 80% of full load. Required load to operate the best during night time is 100%, right? This is the given input. We need to find out the energy requirement first. The very first step should be energy required. Don't jump to the power directly, okay? That you later on you will be going to confuse what we should take a step. Always for the battery, always reach or hit the energy first. So given load, they will operate for 9.5 megawatt, right, across the day. So daytime, as I mentioned, 12 hours of operation, 6 a.m. to 6 p.m., right? And the night time, 12 hours of operation, 6 p.m. to 6 a.m. next day, right?
Okay.
And 4.5 megawatt for the across the night. So energy required is 9,500 kilowatt, right? Into 12. This leads to your 1,14,000 kilowatt hour, nothing but 114 megawatt hour, right?
Okay.
This is your actual energy need for the daytime, correct?
Yes.
Now, what would be the energy need for the night time with respect to 4.5?
Yes.
For 12 hours, this is the energy need for night time. Every day they do require 114 megawatt hour for a daytime, 54 megawatt hour for night time. And for the battery charging load, the constant load is
4.5.
4.5, right? Total energy required. How much for a day to get it operate? Just sum it. For 1 day, 168 megawatt hour. Now, as 80% of load in the daytime will going to operate on the solar plant. So energy required for your solar power plant to operate on the daytime is how much energy you need to generate?
80%.
Yes.
80% of total need. 80%
Yes.
of daytime total need, right?
Yes.
So 91.2 megawatt hour. And the energy required from the grid to operate the daytime load would be
22. Yes.
right, 22 megawatt hour. That would be coming from the grid. Once you reach to your energy requirement, step for your battery calculations. Okay. So the flow of calculation would be helping you out to take a judgmental decisions. Okay. So energy required per day to operate the nighttime load is 54. How this comes? Right? Energy required per day to operate the nighttime load is 54 megawatt hour. Now we have few considerations because we are considering the battery right now. We are selecting the battery, right? So defining the battery capacity. When we are reaching to the battery manufacturer and asking, I need to store 54 megawatt hour of energy and suggest us the right battery configuration. What they will say? They will show you different battery configurations. This is the battery, this is the battery, this is the battery with respect to price, with respect to their operating capabilities. And you need to select one of them. How you are going to select? Now, there is a condition for you. Is 10 years it must operate, correct? And every day you are doing the one cycle of the battery, correct? So 4,000 cycles. So across the year, if you consider 350 or maybe 360 days of operations, okay? So how long the battery will go? Let's say every day one cycle. So every 1 year, there are 365 cycles, right? Even you multiplied that part by the 10, then it goes to 3,650 cycles of if you operate it for 10 years, right? So here battery life is more than 4,000 cycle, correct? Are you getting this?
Yes, sir.
Now, after 10 years down the line, right, you need to consider the factor of SOH. So battery SOH is 90% of its capacity after 4,000 charging discharging cycles. The input coming from your battery manufacturer with respect to the lab report. After 10 years, the battery manufacturer is saying that battery will reduce its health from 100% to 90% only. So you need to consider that factor on the first day when you are planning for the battery capacity. And every day, only one charging discharging cycle is going to be happen. The battery operations is going to be happen with a 25 degree centigrade temperature at the DOD of 85%. This is the condition need to maintain while you are operating the batteries, and this input shared by the manufacturer. This is the condition, right? On a 25 degree centigrade, it must be the environment temperature for the batteries, and DOD would be 85%. The round trip efficiency of the battery is more than 95%. Okay. Round trip efficiency, the charging discharging cycle, and its efficiency. So that efficiency is 95%. Focus here, what parameters for the battery we are considering to define the battery capacity. One is its life, because they asked us for the 10 years of operation. Then we are considering at the 10th year, what would be the health degradation, right? And every day, how many charging discharging cycles are going to happen? Their operating conditions, at what DOD we are going to drill it down, and the overall efficiency, which is round trip efficiency for the battery. And then
Okay, excuse me. Yes, I have a question regarding the point number II. Okay.
Okay.
Number 2. I'm asking about the state of health is 90%. It is an assumption, or it shall be one of the requirements when I require the battery.
So you are asking about SOH, state of health?
Yes.
Okay.
What make it mandatory to make it 90%? How I can guarantee it will be 90% or it will not be 80% or something less? Shall I ask it from the battery manufacturer?
Yes. Like for panels, the similar you are asking for the solar panel manufacturer. They are saying at the 25th year, the entire generation would be reduced to 80%, right, of its capacity. Correct?
Okay.
The similar approach. The manufacturer will give you this graph, basically, the degradation graph.
Okay. And regarding the point number IV, I'm asking about the depth of the charge is 85%, so I shall oversize the battery capacity by 25%?
15%.
15%, sorry. Yes, 15%.
Yes, because you are usable, or you can draw only 85% only, right? Because it's a DOD recommendation from the manufacturer. Otherwise, if you reach to, let's say, get it fully charged 100 and drawing out 100, it will impact on your life of the battery.
Okay.
So effective use of your energy is only 85% of its full capacity, right?
Okay.
That you need to consider on the very first day.
At the factor 95.
Yeah, this figure can be go up to 90, 91, 92, sometimes 95, but very rare chance. But always manufacturer suggesting go this value by 85%. So this inputs you need to ask for the manufacturer, right? Manufacturer will suggest you, sir, you should operate by 85% of DOD, should operate by 90% of the DOD of the battery, not more than that. Okay, they will suggest you on it. And the round trip efficiency will also get this part from the manufacturer. Now, you wanted to power your factory in the night time with the energy of 54 megawatt hour, correct? This is the energy you need to draw out from the battery. Now, your overall battery capacity is equal to required output energy divided by charge discharge efficiency, depth of discharge, and state of health. You know this formula?
Yes, sir.
Putting the value at the below the numerator, right? Sorry, denominator. 54 divided by 0.95 multiplied by 0.80 multiplied by 0.85 by 0.980, right? Is equal to this ratio leads towards 74.3034 megawatt hour. This is what the storage you require, and then only you can draw out 54 megawatt hour in a normal scenario. And at the 10th year also, you can easily draw this energy. Okay. For the battery, don't think for the first day. Think for the last day they wanted to operate. And then plan for the storage. Again. So this is for a 1 day. And they asked us for a 1 day autonomy. Means if I am not able to charge the battery for 1 day, it should power my plant without any failure. So you need to add, you need to sum another capacity, which is, this is your base capacity, right? You calculated here, and additional 54. Why? This is the energy you need to draw out on the next day. Correct? So 74.303 plus 54 leads to 128.303 megawatt hour. 128. So this is your exact battery capacity you need to plan for. 128 megawatt hour battery capacity. So this will help you out at the 10th year with a 1 day autonomy additionally. Like daytime you get it charged, the battery you can operate for this night, and if on the next day, let's say plant was shut down, it was off because of maintenance or any major problem, even that scenario also you can power your factory in the daytime on the next day with this much of energy, 54 megawatt hour. Got this? Guys, are you getting this?
Yes, we are with you. Okay.
All right. Just give me feedback because I'm not able to see your names or maybe faces, but because I'm facing to screen directly, give me feedback when I'm asking.
Yes,
Okay.
actually, the ones who are attending is Muhammad Omar and Gada and
Okay.
Minna. Okay, but we are all joining from Gada laptop, so you will find me only the only
Okay.
mail. Okay.
No worries, but just give me the response so that I can understand there is something going
Okay.
on.
Okay, no problem. Okay.
And we are going to select the battery chemistry here, lithium ferrous phosphate, because I personally, let's say, experienced with the same. So I know the what I can say, operational scenarios and conditions and the sustainability of the battery. And this is a very trending chemistry right now in the market for higher temperature to get it sustained and for the longer life. So we are going to select lithium ferrous phosphate from the Sun Group containerized solution I am planning for, okay, for this problem statement for this case study. So container solution with the model of ST2752UX, okay, US. This model I am planning for the Sun Group. Even you can refer this model on a Google. You will get all those details of this datasheet. Okay, what I referred. So each container for this model will be having storage capacity of 2752 kilowatt hour of battery, right? And then battery voltage, the range is 1160 volt DC to 1500 volt DC. Now I know each container can save this much of energy. How much I need to store? 128 megawatt hour. So what should I do now? I need to require this multiple of this inverter. So how many containers do I require of the battery? There are 47 numbers. How I calculated this value? 128 megawatt hour. I converted it into the form of kilowatt hour. 128,303.406 divided by 2752 gives me 46.62. I can say 47 container I do require for the plant. And I'm keeping that 47 container on the site. Right? So till now, what we done with? We understand the energy requirement for the daytime, nighttime. We calculated the entire battery capacity. We found out one suitable containerized solution, and we calculated their quantity also. Correct? Now, we need to find now towards the PCS capacity. What PCS capacity do we require? Because during the night time only, Bess will going to operate. Bess will going to discharge during the night time. Correct? On the daytime, Bess is under charging mode. Right? So continuous power requirement for the night operations is 4.5 megawatt or 4,500 kilowatt. This is the continuous power requirement for the plant. So we need to select inverter, or maybe you can say PCS, whose rating is more than your required power. So as we know, the PCS is not getting overloaded, let's say 80-90%, right? So what we are doing here, PCS size is 4500 multiplied by 1.20, right? So that we can say the higher rating of the inverter, similar to the inverters. Like inverter basically on the solar side probably getting overloaded, right? But here you don't trace stress the PCS. You operate it up to 85%, 90% of loading on it instead of their full capacity. This PCS having the capacity of 5.5 megawatt, which is let's say 5,500 kilowatt, and we are needed the power of 4,500 kilowatt. So it comes to 20%, like 80% I'm stressing on it, not 100%, right? If I operate with this single unit. So selected PCU rating is 5.5 megawatt, or you can say the 5,500 kilowatt. We select Sungrows this model, okay? SC5500UD. And here, if you look at total number of PCU, we consider 2 are adequate to manage the loading on it. So total PCU capacity is 5500 multiplied by 2 is 11,000 kilowatt. Now you tell me why I consider the 2 numbers of PCS.
Actually, I was about to ask you why we choose 2.
Think on it. Why I choose 2 number of PCS? Because only one PCS can manage my work on the night time.
Yeah. Is it for a backup or something like that?
You are little bit closer, but just give me some more elaboration on.
I mean, it is like a spare or something.
Not a spare. It is connected always. Not a spare. But it will help you in your integration. Yes, the first part is reliability. Second, there is second approach also.
So I need reliability even though the size is not that much.
Yeah. The point is you're investing more on the battery, right? And you're putting huge funds on it. And if you look at the cost competition, the PCS cost is very lower as compared to your entire battery cost. And let's say the selected PCS has some fault, offering some fault. At least your other PCS should activate, or even it will manage entire load for some time, right? And second approach for this is you are thinking only on a discharging mode, correct? When I'm discharging the power, my single PCS can manage. But have you thought about the charging time? When you are charging the batteries, have you think around it? Does a single PCS, let's say single PCS is ready to give the full capacity, but does the battery will accept the same with the same power? We need to think both the ways, like while charging, while discharging. Within the discharging, thus two PCS will help you out to make your system more reliable, more robust. But while charging, what is the scenario? And you are going to charge your batteries from the solar, not from the grid. So solar power is not a continuous, it's an instantaneous, right? And which coupling you prefer? Because we are not moved right now for further calculation. Just tell me which coupling you prefer, because initially I shown you one their existing layout. So which coupling I should prefer now?
AC?
Be confident. AC or DC?
AC.
AC, right? We are going to with the AC calculations, AC coupling system.
Yes.
So while charging, if you look at the solar capacity and their generations, because till now we have not calculated the solar plant capacity.
Yes.
Correct? We are right now up to only energy requirement, battery storing capacity, and their discharging part, right? While charging, what is going to be happen? We don't know till now, right? So considering
Yes.
two PCS is helping you out in the discharging mode with the two approaches. One is more reliable, the solution is, another it will help you out to handle the stress from one device to another. During the operations also, you can operate your what I can say, devices with a lower stress. Like you don't want to operate with it their full capacity during discharging. They can operate only, let's say, sometimes 2500 shared value, right? With their 0.5 C rating, we can say, with respect to PCS, okay? But the C rating not defined only PCS power. C rating defined combinedly with respect to PCS and the battery. Okay.
Actually, I didn't get I get the point of reliability, but I didn't get the point of the AC coupling. Can you repeat it? Because
AC
I
coupling.
didn't understand why the using of another PCU will help in the coupling point. I didn't
No,
get this
coupling point and then PCU is a different, two different points. I frequently just ask that question.
point.
I
Okay.
just got that and then I suddenly asked that.
Okay. So
Okay.
you agree with me that the AC coupling is the most convenient one?
Yes, for this plant, for this AC coupling is most convenient and then preferred solution because they have their existing operations.
Okay, so the scenario that will happen that the PV plant will charge the batteries, okay, from the power of the AC will come, the power of the PV plant will come
Correct.
through AC, and it will be converted again to DC to charge the batteries.
Correct.
Am I right?
Correct, exactly.
Yes, and the other power that comes from the PV plant, it will go directly to the load.
Towards the load. That is the expected thing, right? That is the expected thing because we have not seen that picture right now. Okay.
Okay, because we didn't know
how much capacity of the plant we require, right? So till now you
Okay.
clear this. 2 PCU we required for making more reliable the solution
Okay. Okay.
and handle this stress.
Okay.
Now coming to interesting part, solar capacity. Okay.
Mhm.
How we are going to calculate this? What is the energy need? Right? This is the reference point for us. Energy required per day to operate the daytime load is, we calculated this part in the first slide, right? If you remember.
Yes.
And to charge the Bess during the daytime, how much energy we required? 54 I need to store into the battery, right? And this much energy I require to power my load, 80% of load. Correct? So totally, how much energy do I need to produce from the solar power plant is 145.2 megawatt hour. This is what I am expecting the generation from my solar power plant. And then I need to define if you calculate the system based upon your initial thought directly, right? 80% to reduce down the load, then might be your plant was undersized. Because you are not considered the battery energy which you need to produce from the plant. So what we did here, we want to generate 145.2 megawatt hour of energy from solar power plant. This is the target, and you need to then design your power plant capacity. What could be the plant capacity in your terrain? Can anyone suggest? Because for, let's say, Indian scenario, what I considered in India, average out, okay, for the specific production, I just run this PV system for the simulation. So I refer that 4.5 kilowatt hour per day per kilowatt peak is my generation. This is specific production from 1 kilowatt of power plant in a 1 day. This much of energy I can abstract from 1 kilowatt power plant in a day. So I need this much of energy in 1 day. With respect to that, what I did the calculations. Solar power plant capacity for 145 megawatt hour. So 145.200, that was I multiplied with 1,000 to make it in kilowatt hour, divided by 4.5, which gives me 32,266 kilowatt peak, nothing but 32.267 megawatt. This is what my targeted capacity of solar power plant. DC side I am speaking. Now, what is, the generation you are considering at your end, or the simulation resulting it out in the terrain which you are looking after to plan, like Egypt and subcontinent of Africa? What is the specific production?
So we will need 32 megawatt peak from the PV plant.
Yes, this is the power. So
Yes.
my question is for you, I mean, in your areas, what is this specific production? For India, it is 4.5, roughly.
In Egypt, I think it's from 6 to 7.
6 to 7, okay. So then your capacity would get reduced down.
Yes, الانرجي
Right.
he's asking about excuse me for 1 second. وبيسأل عن كم كيلو وات اور بتطلع من كيلو وات بيك في مصر. ايه 1600 ايه 1600 ده انا بقول له 6 ل 7 في اليوم.
لا بريد.
طيب اسمع
Hello.
Hello, yes. Actually, I was wrong because it is 1,600 per year, so it's 4.3 per day.
4.3.
Yes,
So
actually,
then the
4.3.
capacity would be, let's say, more than this.
Yes, it would be the same, yes, as India.
Yeah, close to same, or maybe 35 megawatt roughly,
Yes.
right? So this would be the capacity on the DC side. On the solar panels, you need to connect with the 32 megawatt. Now, because we are planning this plant as an AC coupled plant, we need to plan for inverters now. Correct? We're done with the DC. We need to plan for the inverters to make that DC power into available AC power. So we know very well that inverters can be overloaded up to 20-25%, or even sometimes 30% based upon the manufacturer's input. So here we are doing the 25% overloading on each inverter. Okay, because we calculated the DC side first. So the actual solar inverter capacity is 32.267 divided by 1.25, because I'm overloading 25% on each inverter. So this value is coming to 25.81 megawatt. So in kilowatt, 25,810 kilowatt AC. This is the inverter size I'm planning for. Okay. Now from here onwards, you have two options. Whether you can go for central inverter of individual one megawatt capacity or 2.5 megawatt capacity of each, or you can go for a string inverter. It's a choice based upon the site conditions and scenarios, as well as how commercially you are closing the deals with your vendor, right? So here I did consider the string inverters part. The rating is 350 kilowatt. String inverters 350 kilowatt. Okay. And consider the same rating from this manufacturer is Sungrow, because why? I deal with him as I'm considering a combined solution from them. So the source company is similar, so I can deal, let's say, commercially a viable solution for us. So I consider 350 kilowatt, and technically it serve my all the requirements. So SG350 HX model I considered as a string inverter, because a single string inverter is serving 350 kilowatt. So how many numbers would be 25801, right? 25 megawatt you do require. So 25,810 divided by 350. Each rating of the inverter is 350. So it gives me 73.74, nothing but 74 numbers of the string inverters I'm using, right? So there has been, I think, 45 containers of the battery and 74 numbers of the string inverters, right? This is my requirement, or the quantity of the inverters. So we know the inverter input voltage range, they stated with their catalogs, okay, 500 volt to 1500 volt DC on the input side. Hence, we can create the string up to 1500 volt DC. Now I am doing the string calculations, okay? Be focused. We're done with this number. We're done with this numbers: inverter total capacity, individual rating, and quantity of the inverter. Now we are moving forward for calculation of the string sizing. So each inverter will bear the DC capacity up to. Hello.
Yes. I'm sorry for the interruption, but I have a question regarding the 1.25, the DC to AC ratio. If I'm going to choose another ratio to be 1.1 or 1.2, is it applicable, or why do we choose?
No, it is applicable. You can consider based upon overloading, how much overloading you allow on the inverter. Okay, overloading, like inverter rating of 100 kilowatt, and I'm connecting on the DC side 125 kilowatt.
Yes.
This is the ratio you can prefer. I mean, whatever the manufacturer will suggest you can apply, and based upon your understanding too, the experiences part. In general, 20-25% overloading is okay on the inverter side. So you can reduce this number also. Based upon this number is going to be varied. So each inverter will bear the DC capacity of. I am just doing the reverse calculation now. This is my DC capacity.
Yes.
And divided by total number of inverters. What I got? 74. So every inverter equalized on it, right? On the capacity. So 436. Their rating is 350. So on the each inverter, I'm connecting 436.05 kilowatt. Correct? You got this? This number 436.05. Now, here I'm considering the panel. I'm taking the panel from the Trina Solar, the 490 watt peak tall max Trina model. Okay. And with respect to the data sheet, they have given me the maximum power point voltage is 36.5 volt. That is VMPPT. And maximum power point current is 13.43 amps. That is IMPP. And then open circuit voltage is 43.4 volt. This is the input I considered from the data sheet of this tolerance. Now I need to calculate the string sizing and then how many strings I'm getting to connect with the each inverter. So the maximum voltage input to the inverter is 1500 volt DC, right? For every inverter, they have range in the range of 500 volt DC to 1500 volt DC for the inverter. Okay. And then maximum number of panels in each string. How I can calculate with respect to VMPP, right? Maximum power point voltage. So 1500 volt DC. So this says divided by 36.5, 41.09, say 41. So we can plan the number of solar panels in each string below 41. So 41 is your threshold limit. Don't go beyond that, right? Every string would have maximum of 41 number of panels, not more than that. Otherwise, it will exceed your limit. Now, let us consider. So, how I get this 37 numbers of panels in each string. So, I did the iterations, okay, and I found out that 37. I am going to consider 37 number of panel in each string, and I'll connect. And I'm just checking the voltage here. 37 into 36.05, 36.5 for this VMPP, right? Connected in the series, right? Every panel in series. So this gives me 1350.5 volt, and it's in a limit like 15 below 1500. So that would be fine. So I'm considering 37 panels in each string. So each string capacity would be, this is the wattage of the panel, each panel 490 multiplied by 37 gives me 18.130 kilowatt peak. So every string carries 18.13 kilowatt peak. Hence, the maximum number of strings can be connected to the inverter. How many strings can connect to the inverter? Because each inverter is catering this much of DC, right? 436.05. Each string can carry this much part. This is giving me 24.05, say 24. Okay. So I'm connecting 24 numbers of strings. So the point is, there is only 12 numbers of input strings in lead port. And this is given from your
Inverter data sheet.
Inverter data sheet. Because input port is only 12. So what you can do, you can use the Y connectors over there. And you can club two strings in each so that you can manage this 24 strings over here itself. Okay. Hence, we need to use the string connectors, right? Y string connectors, and so that this capacity can be managed. So
what about the current of it is 30.43. So if we are going to add 13 by
26, it will be each port will be 26.
It will be, let's say it will be multiplied by 24.
Correct. No,
Yes.
it will be going to be sum, right? Exactly. The summary wise, it is multiplied by 24.
Yes, so it will give
13.43.
yes, 322 ampere. So how can I guarantee that the inverter will withstand this current?
Sorry, come again.
How can I guarantee that the inverter will withstand this current, 322 ampere?
322 ampere. So what you did, you multiplied by 24 by 13 point, right? 43.
Yes.
And what is the rating of inverter?
The rating of the inverter is 36 kilowatt.
350 kilowatt.
Yes, 430.
No, your inverter output is 350. We are
Yes,
connecting
350.
DC side is
Yes,
236.
Yes, 350 kilowatt AC, yes.
Right, 350. Now we do one calculation. On the DC side, 350, and they are okay with the voltage of 1500, right? So do one thing, 350 multiplied by 1000 divided by 1500. So it's 1.25. So 3,000 and 500, right? 3,500. Sorry, 350 divided by 1.5. So it gives you 3,500 divided by 15.
No, 350 divided 0.8.
No.
Here is
No,
the
no.
voltage.
No, you just calculate. See, you just need to compare the ampere, right? Whether it is going to sustain or not. So you are very well aware that on a summary, like 24 number of strings you are going to connect, and the each what I can say, the string will give you the current of 13.43, correct? Because in a series, the current would remain same or increase. What happened in the series? What will happen in the series?
The current will remain the same. So I have these strings will produce around 322 ampere. 13.43 by 24.
How
Okay.
much it is? Right, 24 by, right, 13.43 by 24. How much it comes?
It's around 322 ampere.
25 250 or plus give me a minute. 240 sorry, 250 plus yeah, about to 320 something, right? 320 amps, something like close to that, correct?
Yes, correct.
So this is your current.
Input.
Now,
Yes.
now you just check your capacity is 350, correct? 350 kilowatt. So power is equal to V into I, right? Do this calculation. Power is equal to V into I.
Yes, which voltage?
Now voltage is 1500 you need to consider.
But the 350 kilowatt, it is at the AC side. So 350 kilowatt.
On the DC side, see, on the DC side, you can consider like 436 into your 1500. I mean, 436 into 1000 divided by 1500. Like it's a 2 by 3, and here 350. Then it gives me yeah, it can manage. You do the calculation. Just a minute, I am doing the calculation.
190 ampere.
I will do my calculation. Give me a moment. So your 13.43 multiplied by 24 gives you 322.32. This is your total amps, and now you are operating on 350 kilowatt. Multiplied this part with the 1000. and sorry, it's a 436, right? 436.05 multiplied by 1000 and divided by 1500. It is giving 290. And how much current you are getting right now? 320, right? So 290. If you did this calculation with respect to 1000 volt, sorry, 1000 volt, how much it comes? 436.
Yes, 346.
436. If you did this calculation instead of 1500, it is operating, let's say, 1000 volt. Why I am doing this? Does your irradiation is always it full of capacity or not? No, right? It's instantaneous. So the voltage which your string is going to achieve is not always 1500 volt. It is less. Correct?
Yes, correct.
And that's why your current capacity can managed. If you reduce your 1500, let's say reduce up to 1200, even in that scenario, your capacity is managed. Got it?
Got it, yes.
So this is how you can optimize your plant. Otherwise, what you need to do, you need to enhance the number of inverters.
Yes, it will be increased, yes.
Right? So that's the scenario. And so this is again I did the reverse calculation, okay, to just showcase what exactly the plant capacity would be. If you look at what I did, each panel rating multiplied by individual count in each string, right? The number of panels in each string. There are 24 number of strings in each inverter and there are 74 inverters, correct? I will show you, I'll explain you again. This is the panel wattage, like 490. Each panel wattage is 490 watt. So I multiplied by divided by 1000. So it is kilowatt multiplied with the number of panels in each string, right? This gives me each string rating multiplied by total string. This gives me single inverter rating and multiplied by total inverters. This gives me plant exact output, right? So this is a DC, exact DC. Initially, how much it comes? Like here, 32.1988 megawatt, right? Initially, how much it was on the last page? 3267, correct?
Close enough.
Right? So it's a 267. And on the next page, if you do at 32.198. So if you reduce it, the value is not much, right? The difference is not much. .267 for your reference, 267 minus 198. It's 1690, or you can multiply this into 1000. So sorry, 0. So it's a 690 up to 700 only. So 700 kilowatt is the variation in a 32 megawatt capacity, right? So this is your optimistic value. You can put this much capacity of the plant only on the DC side. And in summary, I wrote here, there are 74 inverters. Per string, there are 37 panels. String per inverter, 24. Panel rating, 490 watt peak. Inverter rating, 350. Panels per inverter, 888. Number of panels I connected for individual inverter is 888. Got it? So this calculation you need to try at your own. Okay. This is the result I stated here. Should I move? Shall I move to the next, guys?
Yes.
Now we will move forward because till now what we have done with, we're done with the battery capacity, we're done with the TCS capacity, we're done with the solar capacity, right? DC side, we're done with the inverter capacity. Now next to the inverter there are ACDGs, right? I need to club it all together and I need to merge somewhere so that my load is going to be operated. Now what I need to do, I need to find out the ACDB calculations part. So on the inverter output AC, which is 350 HX, the output voltage is 800 volt. They stated as the data sheet. 800 volt AC. Okay. So now, and maximum output current is 254 amps. 254 ampere AC. So this is what the output coming from your inverter. And we know switch gears cannot be loaded more than 95. In generally, it was loaded on 80%. We need to find out the rating of switch gears for individual inverters, which you are going to tap. What we did, we find out the required switch gear, or you can say the MCCB rating, the full load current multiplied by safety factor. So full load current we get directly from the inverter output, which is 254. This is from the data sheet. Okay, 254 into 1.20. So considering 80% load overloading on, this gives me 304.8 amps. So I can roughly, I can go to the catalog for the MCCB and select this MCCB of 315 amps, 800 volt AC. This MCCB I selected for each inverter. Okay. Now, important thing. Hence, we will select this closest higher rating, right? We will go 1 ACB for every 10 number of inverter. This is the panel which you need to plan and club. How many inverters you wanted to club in a single, let's say, ACDB. It's your choice. It's a designer perspective. I thought here I can go with, let's say, 1 ACB with a 10 inverters. So if I look at the 10 inverters, the capacity would be 3.5 megawatt, and that is good enough, right? So individually, like 350 kilowatt of each inverter, 350 into 10, this gives me 3,500. So 3.5 megawatt, I would say. This is the capacity. With that, I am considering 1 ACB. So with reference to that, if I select 254 as in full load current from the inverter multiplied by 10, so this is giving me 2440, like 2,540 amps. And again, the similar principle, the loading on the ACB won't be more than 80%. The same thing I applied here, 2540 multiplied by 1.20 gives me 304.48. So I reach out to the catalog and I find out that at 800 volt AC, 32 amps of ACB is available, and I selected this. Okay, so this is the single ACDB 800 volt. The summary of that, like MCCB rating is 315 amps, MCCB count like 10, ACB rating 3200 amps, ACB count 1, spare I maintain 2 additionally. So the panel is 10 incoming, or let's say 12 incoming and 1 outgoing. 12 incoming. Within that, 10 has been equipped with the inverters and 2 would be in a spare. So this is the panel what I'm planning for. Okay. Got this with the ACDB part, how we can summarize and see the minor detailing, right? Because you are dealing with right now the big plant. So including like your ACDB includes like MFM, footer, then indication lamps, the internal control wirings. Then that engineering, either you should have your own activity or you can ask your supplier to do the same. They will suggest you on it. But on broader term, you are aware about how much incomings are there, at what rating, and what is the outgoing. So here 12 incoming and 1 outgoing. Got it? Because you are coming from the solar side, your generation side. Got this?
Yes, we got it. So
No.
actually, the one question regarding the 10 number of inverters, it is from our choice or
Our
it is
choice.
based on the capacity of the transformer?
No. Oh, it's our choice, but again, you need to find out whether, let's say, you can club 24 or maybe 20 number of inverter in a single ACB. But after that, whether that particular ampere ACB is available or not, you need to check, right? If let's say you club it 20 numbers and there is no ACB available, then what you need to do? You need to again recalculate. Correct?
Okay.
And because of that recalculation, you will be realizing that 10 would be the good fit. Because if you observe on a ACB side, I think there are 5,000 amps of ACBs available. Right? You can go up to that. But next to that, will it be possible to go for? That would be the question. So you can plan it. I mean, being a designer, you can plan it the quantity. And so I planned with the 10 quantities. Now, let's say this is operating on 800 volts. Okay. Now, I am going to select the transformer from here onwards. The output of ACDB, the full load current is 2540 and operating voltage is 800 volts. Select the transformer, right, for this much of load. So actual amp, I need to find total amp into load factor divided by diversity factor. As we know, we are dealing with the power plant side. So load factor and diversity factor should be unity. So 2450 is your actual ampere. You can find out the transformer kVA, like √3 V actual amp upon 1000 into cos phi. √3 voltage is 800 volt, 2540 divided by 1000 into 0.95, right? Equal to 3519527.241 divided by 950 is equal to 3704. This is the kVA of the transformer you do require. 370. For ACDB, don't be surprised. We given the calculation for a single ACDB. Okay. Then you told me how many ACDB required for accumulating 74 numbers of your inverter. How many ACDB do you require? Total ACDB count. This configuration for single ACDB. Correct? So in total, you do require 8 number of ACDB. I summary here mentioned here. Mark the summary here. Like total ACDB are 8. ACDB rating individually 3200 amps. So grand total count of MCCB is 96 in total. Right here it's at 12. Usually 96. 12 into 8. Spare MCCB 96 minus 74, 22 spares across the plant. Okay, this is the summary. From here onwards, I am going to select the transformer for each ACDB. Okay, so I'm summing it. A transformer capacity coming to 3705. Now consider the safety factor 1.2. So this leads to 4445.712. So I go to the market and select the capacity of the transformer as a 5 MVA transformer, which is closest and nearly available in the market. So we do select the transformer of 5 MVA. On the LV side, it is 800 volt, and HV side, it's a 33 kV. This type of transformer I do select. Okay. Have you got this? Guys, are you getting this?
Actually, yeah, for
Okay.
for high tension panel, yes.
Okay.
But I didn't get the 50 kiloampere. Is it a default level? 50 kiloampere
50 kiloampere. Sorry.
default level. The 630 ampere at 50 kiloampere. No. The next slide.
Next slide. Okay.
Yes, the point number 4 at the right.
Okay.
For
This.
high tension panel.
This is the safety factor. Like you are giving the loading on the transformer is 80% of its capacity, right? And that's why
Okay.
we multiplied by 1.2.
Yes, I'm asking also about the breaker because if you remember the latest session, you were saying that the sizing of the circuit breakers, I'm not talking about the transformer, I'm talking about the sizing of the circuit breaker. You are mentioning that it is
Of this value,
600.
I'm coming here. I'm coming here. Okay, wait. I'm coming here.
Okay.
You're done with
So
this?
Okay.
You're done with this?
Okay.
Have you got this?
Yes. Yeah.
Okay. I think lastly you asked this question, right? 600%. The point
Yes.
is, I found that this 600% is applicable on the low plant capacities, okay, where the rating of VCB is not available. I mean, the lowest rating of the VCB is not available. That is why it comes to 600%. Okay. On the higher rating, it is normal practice. It states it is ranging from 150%, like 50%, let's say 1.5 times, you can say roughly. Okay, like 150% to, sorry.
Okay. 1.5 to 150 to 600. So it's 150
Yes.
to okay.
Yes. 150 to 600. That's the normal practice.
Can you tell me the reference that you found?
Which I yes, it is. You can refer like the normal IEC 6200. Okay. 221. You can refer that. No worries. That is stating similar to switch gears. Okay. Similar to switch gears. What we are following, the 80% loading on the switch gears, correct?
Yes.
In the same fashion, you can carry out that activity. Then if you follow that, how much it comes? 125%, right? Yes. But because of HT side, because of this is on ST side, the people are following 150%, right? Little more than that. Okay. The standard is saying you follow the switchgear practices. And it is stated that 1.25 is good enough number. Okay. But the common practice says people are, because they are dealing with the ST and they don't want to have any issue with the ST side. So they follow 150%, that is 1.5 times. And because this 600 comes, because it's on a low ampere and there is no switchgear available, right, on the lower side. And that's why it comes to 630. So if the current rating is lower than, let's say, 100, right, the 15 amps or 16 amps or maybe 50 amps, then if you choose to 630, then it goes to 600 times, the 6 times more than that. That's the scenario. Okay. You got the judgment on it.
Okay.
So here also the ampere, if you look at, because of 33 kV, it is less than 100. And that's why, and there is, let's say 400 amps of VCB is available, but which is non-common, right? 630 is a common figure available in the market. Correct? And that's why it comes to calculation of 600%. But if the 400 is available, you can go for that. That's the choice which designer can do. But readily available product is for 630 amps. So here it may be in the ranging of 150 to 600. So that's why you can say 1.5 to 6. That range you can apply. So ultimately the lower side limit is 1.5. Next you can use whatever is available. And for this transformer, let's say this is a 5 MVA transformer. With respect to that, there is a single VCB I used, and there are total of individually how many transformers would be there? 8 number of transformer, right? So 8 number of VCB we are going to tap. That's why VCB count is 8 on the solar side. Okay.
Okay.
Now there are 2 more transformers we need to select and where they are going to use. Before this, addressing this, I'll just show you the outlay so that you can realize that where we are and what is the remain portion to address. Okay. See, we have calculated the solar side, we have calculated the inverters, we have calculated with the ACDVs. We have done with this transformer, we have done with this individual VCB part. Now we are clubbing it to your main existing, or I can say the upgraded transformer. We are just tapping with this, right? This transformer is having the capacity, let's say 50 megawatt with a 33 kV on this side and 132 kV on this side. Okay. And now you reach to here. You are done with this part. Correct? Yes. And also you are done with this and this too. Correct? Now we are dealing with to calculate these 2 transformers, this transformer and this transformer. We are remain to calculate these 2 transformers. And here we are going to calculate that. Okay. So these 2. Later on also you can correlate with respect to the images I attached, the similar images I used in the diagram. So you can remember which calculation can be belongs to the which part. Okay. So you can correlate easily.
Okay.
So the transformer selection for your PCU to the grid. PCU to grid. So the output of your PCU connected to the grid side. Now full load current. How from where it is coming?
The number of transformers at the AC side of the solar power panel.
A number of transformers on the AC side are 8.
All right.
This is PCU to grid, this value. If you look at this transformer, where it is connected.
Okay, so why do we I select 4?
So I'm asking you that.
And why is the operating voltage is 500 volt AC, 550?
That is what I'm asking you.
Yes, is that the existing equipment that is found at the grid side?
This is the output coming from your PCU, because we are connecting to PCU, right? PCU is the source. So PCU output is 550 volt AC.
Okay, it is okay. It is from the PCU. It is so the number
PCU.
of yes. Okay.
Got it.
I was talking about the DV plant side. No, for the PCU, I believe it is 4 years because.
And this is the current value of the PCU. And why this 4? Because in the internally PCU has a 4 DC inputs, and it has each rating divided with the same, right? Each if you refer this diagram again, give me a moment. What I can do best for you is
Yes, sorry, we lost connection for some seconds.
so this is the data coming from the PCU. Okay. I'll share that data sheet so that you won't be get confusion on it. So where these figures are coming out. This is the coming from your data sheet of PCU. Okay. And you need to select the transformer next to that. So the actual ampere, which is 6348. I think my voice is getting echo. Right now it's fine. So the transformer KVA is equal to √3 into voltage into actual amp divided by 1000 into cos phi. I'm just putting the numbers. So this gives me 6108 KVA. So the loading factor is again 1.2, 1.2, right? Like 80% loading. Then they are giving me 7329.6 KVA. I'm dealing with the 7.5 MVA. Like the PCU is 5.5 megawatt, right? Correct? 5.5 megawatt PCU. And I'm leading that PCU next to it, the transformer of 7.5 megawatt. So it can manage easily that 5.5 MVA capacity. And this is a step up for 0.55 kV to 33 kV step up. Correct? So that's why, because there has been 2 numbers of PCU, and that's why I use 2 numbers of the transformer, and the rating would be 7.5 each. On the ST side, they will be getting ampere of 105, right? And then accordingly, they can select the same VCB, what we selected on the solar side. 630 amps of VCB.
حد عارف جاب ال 1587 دي.
And on the other hand, like PCU to load side, PCU to load, okay, you are directly connecting to the load. So if you look at each PCU is of having 4.5 megawatt, selecting 2 different transformers for 2 different PCUs. We know the full load current of each transformer, load upon square root of √3 VA into cos phi, right? Putting the values here. Operating voltage as 440 volt AC, because you are dealing with it directly towards the load. And actual ampere, total amps into load factor divided by diversity factor, the same formula, keeping these values, load factor, diversity factor as unity. The transformer KVA is 2493. So including the safety factor and all, this deals with the transformer capacity, and the transformer is of 3000 kVA. each. Right, 3 MVA, or you can say the 3 MVA transformer you can deal with. Okay, on the load side, okay, on the load side, 3 MVA each. And how much is your load you wanted to operate? 4.5 megawatt, right? And you are dealing with 3 MVA each. So there are two. So total MVA is 6 MVA. And you can easily manage that 4.5 MVA within that, correct?
Right.
And there is a main transformer like this symbol we use there, right? Two winding on the input and one winding out the output. So the full load current, right, for each is 61.5857 into 8. There are 8 inputs coming from the solar side. And the operating voltage is 33,000 volt, like 33 kV. We are dealing on the LV. Its LV is 33. I mean, actually, it's a HV, and it's again dealing with HV. So low voltage and then higher voltage. So dealing with the same, doing the principal calculations again, loading and all, 33.78 MVA. Including your 1.2 factors like overloading, not more than 80%. So that would be a 35 MVA transformer. Okay, 35 MVA transformer you do require. The bigger transformer of 35 MVA capacity, and that is a single transformer you do require. Even you can have maybe spare standby on the field. It's a choice, and even you can manage. I mean, it's a deal with the side functionalities. But
I
here,
have a question.
Mhm.
Why do I use 3 winding transformer?
Okay, you can use 2 winding also. I use this to split the input system, make it more feasible to get it club, to get it installed on the tapping perspective.
So the first winding, the input windings, they oppose come from the PV plants. Am I right?
Yes. This is coming from the PV plants, these two. And this deals with the grid.
Yes, but I had another question. Why do I need to inject the power directly to the grid, and while it will be used directly from the load? Because
Very good question. This is the provision this is the system we are preparing, okay? And now how the operation will going to happen, that we will see. I'll explain with the diagram, okay? Now this is the system. Let's say the system must capable for the worst scenario, right? You are having the solar plant of 32 megawatt. You are having the final transformer capacity of 35 megawatt, correct? Even let's say some incidents, your battery plant won't work, and you for some time you need to push every power to the grid. What you will do then? At least plant should run, right? That would be the target. Plant should operate with its functionality because it's AC coupled.
But if there is a problem with the PV plant, why don't we shut it down?
No. I'm saying the battery plant has facing some problems, and you set it down for the battery. And your entire factory is under maintenance. Let's say the critical scenario. It won't happen, but the system should have ability to sustain within that duration, right? Otherwise, what you need to do, you need to shut down each inverter.
Okay, so what do you mean is that the factory will withdraw the power from the grid?
No. Factory will withdraw the power before it reaches to this transformer exit. Like factory will withdraw the power from here.
Yes.
From here, not from here. Okay. This is the interacting with the main grid. Factory will withdraw the power from the input side of this winding. So here the solar is connected, so solar is stopping here. Your base is there, base is stopping here, and then factory is drawing power from this input itself. So you can directly technically you are getting the input from the solar. Exactly. But
Mhm.
just physical connections are you are drawing the power from the node of final transformer. There you might have, let's say, isolator panels, right? Or the isolator poles, proper isolation yard. And then from that yard, you are drawing out your energy. Okay. And next to this, there is SF6 breaker, and you can calculate it based upon the similar principle, what VCB you are following there. Okay. Here also I mentioned 600, but it's again the similar theory you can approach to. Okay. For 132 kV, 1250 amps. The same calculation, like next to this, what is the current, and then accordingly you can find out its rating. Now, initially in the module 6, we saw this diagram, correct? If you remember with the AC coupled systems, there is a solar power plant, there is a separate isolation mechanism, there is inverters, right? And then there is a battery capacity, then there is their isolations, correct? There is PCU, there is a backup load, the specified load, correct? And this is your connecting with the main grid, right? Here, there is a transformer basically in our system because the system capacity is 2 more, correct? And this diagram is just directly connecting with the cables, but actually on a ground, we need to keep here as a transformer, right? And how the diagram would be, this is the diagram. Like now you check the flow. Battery, PCU is interacting with this, connecting here. Solar plants, 4 inputs are coming, matching here. This is for 4 inputs. And this is your previous diagram. You're again tapping here. Like here, before connecting to this, there might be a yard, right? The isolation panels or isolation or tower, right? You can isolate that. The switch yard would be there before transformer. And then you can use, there is again separate VCBs, then tapping to this panel and then powering to the load. See, now if you remember initially with the problem statement, what they state, the load will going to operate in the daytime from the grid as well as your solar plant, correct?
Excuse me, can you give me the control? I would like to ask about something because during to the.
So what, sorry?
Yes, I would like to ask about the scenario of operation.
Yeah,
Okay.
you can operate, you can ask here, no worries.
Okay. Actually, from my understanding, that at the normal day operation, okay, the PV power plant are going to feed the loads. Okay. Do you see my screen?
No, actually.
Can you give me access, please?
Do you have another problem statement or this problem statement only?
No, I have this problem. No, you can give me access to.
I am giving you, just a minute. I'm giving you. Yeah, I have given. Please check. You can share now.
No. You can share your screen and give me access to edit about to mark about your points. You can share your screen normally, and you can give me access.
Advanced sharing. Just a minute. I have shared with the multiple. Then
because we don't have these slides till now, so you can share. I would like to ask about on this slide.
just a minute. I'm just checking that part. Invite and then remote control. Give mouse and control. Gada, right? Yes, I have given.
Yes. So you are seeing my mouse now?
Yes, I can saw.
Okay, what I'm asking is at the normal day operation at the daytime, the PV power plant will feed the loads from this line like this.
Correct.
Am I right?
Yes.
Okay, and at the same time, they are going to charge the batteries through this point.
Correct.
Okay, and at the night time, the batteries are going to feed the load through this line.
Correct.
Okay, so why why there is another power will go to the grid? This is
Actually, see, you design your plant on the daytime. You wanted to charge your factory with a two different sources of energy. One is your existing solar power plant, another is the grid. Correct.
Okay.
And there is
So
an existing system. Initially, the problem statement itself says there is an existing plant operating, and they wanted to go for 80% of its total load on the daytime is powered by the solar plant.
Okay. Okay, I got your point. So my question is that I size this transformer. This is the transformer
Right.
from
Correct.
the PCU to load.
Correct.
And I'm sizing this transformer. It is
Uh,
from
give me a minute. Sorry, I'm breaking you. If you look
Okay.
at the purple line which I marked, integrated Bess plant with the Bess. On the left side of that purple line, everything you designed. On the right side, it was existing system. Okay.
Yes.
And transformer and let's say S sub 6 breaker might be you need to upgrade, or maybe not required to upgrade because they already having 32 megawatt of requirement. Because of that only they have stated what they asked, 80% of capacity should be powered from the solar, right?
Right. So this transformer voltage level it is from 0. Let's say 0.8 to 0.55.
No, that was because it's a AC, so it's a 0.5 kV to 33 kV.
233.
Right.
33.
To 33. Correct.
So why do I use at the beginning? Why do I use the 33 kilovolt transformer while I shall use go directly from the 0.
See,
Is it from
the output of your inverters is 800 and the output of your PCU is 500. You cannot meet that.
Okay. Okay. I got your point.
Got the point? Because of see, system and product availability, I need to do that. Otherwise, if the similar range is available, then we can club it. And this integration would be solving your complex problems, right? Because every scenario you run on this design, it will be going to pass. If you check any iteration, charging, discharging, charging from the grid, even charging from the battery to the load, even charging from the grid to your battery. Okay, you can run any operation and system will survive.
Okay, I got your point.
Anyone, any query? Any query, guys?
No, it's okay.
You got the scene? Here,
Yes,
till now,
one second.
sorry.
Yes, I wanted. Hi, hello.
Yeah, please.
Yes. I just want you to please clarify to us how did you elaborate the PDF that we sent you to the to the numbers that you mentioned in the beginning, the 9.5 of daytime and daytime load and the 4.5. How did you translate the PDF that we sent you into these numbers? Because the PDF included mentioned some load profile, and so how did this load profile was translated into the numbers of 9.5 daytime load and 4.5 nighttime load?
Sorry. I think there is some misinterpretation. You are referring this example which I referred to your problem. I mean, the sheet you shared with me, right? You are trying to correlate that part.
Yes, I believe so.
Oh. Just a minute. Actually, these two are different thing. I'm sorry. I referred this problem statement from the problem which we solved initially, right? And so this is the, I mean, can you see my screen?
Yes.
So this is the sheet you shared with me, right?
No, I cannot see your screen. Your screen is freezed to the PowerPoint.
Okay. Sorry. Now I'll reshare again. So tender document, right?
Yes, that's it.
It's the same.
Yes, this is what I was asking about.
Oh, exactly. Yeah, I think this will be just a minute. We need to reform the inputs. See, I'll just clear. With respect to this tender, the problem was not okay. Problem was with some other problem statement. Okay, don't correlate this. I'll just check. You can approach the similar methodology. I'll just check, and we will just sort it out. What could be the right, the figure, the megawatt rating. Okay, we'll just run through in the same. Then they have mentioned the expected renewable energy. So it's a 12 to morning 9. That's fine. That would be 9 hours. Ramping linear and this. Okay. They have not stated the kilowatt hours ever. The maximum, that would be fine. The forecast is fine. This is okay. They are not stating any value for the energy consumption and even.
It's a percentage of power output.
No, but what is the final scale? Because this is the document which they are sharing, like percentage they are marked, but at with reference to that percentage, like what should I consider? How much is the final, and accordingly percentage we will going to apply that figure, right? The power output 0.20, that is fine. Percentage, okay, solar plus Bess, and morning 9 to evening 10, right? This is what they wanted to operate. And maximum output 10% of its 100 capacity, and then solar irradiance. But what is the value they are looking at? How much megawatt they are looking at? They have not marked that figure. How much megawatt they are looking for?
we don't have this info because that was the input that we got. I believe we can assume a power and elaborate accordingly the exercise.
Hello.
Yes.
Yeah. So they have not marked the percentage basically. Have you seen the final rating from them?
I believe for our problem for the session we can assume a power, and accordingly with the percentages that we that are mentioned, we can elaborate the exercise.
Yes, actually, you can do the same. The point is, if you do have the final value, the final figure, the kilowatt, if it is there, then the final you can execute.
Let's assume,
No
for
worries at
example,
all.
that the 100% of the power is 40 megawatt. The 100%
100% of the
yes.
power
Let's
is
assume
40
yes.
megawatt.
Oh, okay.
Okay, then and in the daytime also you wanted to operate from the grid, or how it is that? On the daytime, what you wish to operate? Let's say it's a 40 megawatt for 100%, right? In the evening, if I look at this is the profile they wanted to operate with the Bess.
Yes.
Ramping linear. At what time they do require the energy from the battery? Any moment.
Yes.
So ramping up, it's a linear, that is fine. So 9 to 10, if within 1 hour, it's up, it is fine. And then ramping down, that is fine. We know 1 hour, that would be fine. Then it's a zero output. And this is from the solar they are expecting, right? And they are setting the capacity of the solar plant. So 100% of renewable energy for output, which is 10 to 9. So in a daytime, so here basically what you need to plan, you need to plan for and what they're expecting in the night time. Do they are expecting from the base during the night?
The requirement
Because
was that
what I understood is in the daytime, you see, without base you can manage the daytime operation with the capacity of whatever you say, the 40 megawatt, then you can achieve it. Because they are starting from 10 a.m. to evening, let's say 20 to like 10. So the duration you can refer to 4 p.m. up to 4 p.m. Okay. You can
so from night.
you can 4 to or even let's say 6 to 10. That is the power you need to plan for the battery.
Yes.
Right?
From
Let's say
16
6
to
to
20.
10. Maybe
Yes.
5 to 10, 5 to 10 p.m. Right? From 5 p.m. to
Okay.
10 p.m. The 5 hours you can plan for battery, and this you can directly plan for the let's say the solar, right? Up to 5
Yes.
your
So 8
expectation can
hours
meet.
solar and 8 hours solar and 5 hours.
1, 2, 3, 4, 5, 6, 7, 8. Right. 8 hours solars and 5 hours for the battery.
Yes.
So what you need to consider basically the 40 megawatt is its requirement, correct? The full load. Is it the 40 megawatt? It will be very huge capacity for the battery then.
Okay.
Just confirm from them because I don't think so 40 megawatt is their requirement. The battery would be very high. Even let's say 40 megawatt for 5 hours of the operations. So 40 into 5, because it would be the constant supply, right? Roughly. So the
Yes.
40 into 5, it's a how much? 40 into 5, 200 megawatt hour of capacity. Now we have the battery capacity of 120 megawatt hour. But the technically load is how much I am going to operate? The 4.5 for 2 days autonomy, or even here we can consider only 1 day as an operation, like charging and then discharging. Okay, there is no autonomy we consider, only standard practice. Even we can operate for 10 megawatt only, not a 40.
Okay,
Correct?
can you please repeat why do you find this odd?
See, if you observe, like 5 hours to operate from the Bess, right? This is clear now. 5 hours we need to operate because solar won't generate much within this time. Correct? I am pretty sure you're saying just to consider 40 megawatt as a total load, right? But I am thinking the 40 would not be their total load. The load would be little lesser, or little in the sense it might be up to 10 megawatt or 20 megawatt somewhere, not a 40. Because if you see, to manage your entire system, okay, if I'm considering the 40 megawatt as a load, so for operating 40 megawatt for a constant for 5 hours duration, what would be the energy then? 40 into 5, correct? 40 multiplied by 5, that would be 200 megawatt hour. Am I right, Shahrukh? Can you hear me? Hello? Can you hear me?
So I guess she's not in the call, I believe.
Hi,
Hello?
hello.
Yeah, can you hear me?
Yes, excuse me, we lost the connection again.
Okay.
Yes, actually, in this case, we had the RFP as it is, as the PDF that you have, and we had coordinates of the land, and accordingly we designed the PV, and the output was not the 40, was less, was much less. It was around 12 or 13 megawatt.
Correct.
Yes, so
And then you can plan for the battery for up to that 120 and
yes,
something 200 megawatt hour.
yes, exactly. So
So you can
from
correlate. So I mean, I forgot name. Is it Shahrukh, right?
no, this is Ghada.
Gada, okay. So
Yes.
Gada, you can correlate, I mean, your plant size like 12 megawatt, and what we consider here within the reference we followed, that case study, is I think that figures are very close to your numbers, right?
What figure?
The
That
rating of
yes,
the megawatt, like your system, what you're with respect to the
yes, was
10
very
years.
close to the example that you
Yes, that's
explained.
what I
Yes,
covered, right? So
yes,
you can
exactly.
correlate very easily the numbers
Yes,
and then
okay.
putting the figures, and then you can summarize your solution according to that. But within this document, I think might be they shared with you in some other document. They miss the value of stating their profile of power. They are
Because
stating the profile with respect to operational, right? Like at what percentage, but what is the figure with respect to, I should consider the percentage. That
Because
figure
the
is given.
profile of power was left to be estimated according to the land that was available to install the system.
Okay.
They give us some coordinates and a land to and the load profile that is required and needed, and accordingly they requested us to design the solar and the BCS the BESS to cover the load. So we
Okay.
have a limited land and to cover the load and to install a battery energy storage system to cover the rest of load.
But does this stated the load?
No, when we made our design based on the land limit, it gave us a 12 megawatt solar.
Okay. 12 megawatt solar. So it's a DC side. Then AC would be, let's say, 10 megawatt only.
Yes.
So you can roughly consider the same example what we carried, 9.5 megawatt. Even our plant is bigger, like 32 megawatt for the solar plant we estimated. In your scenario, because the DC side is only 12 megawatt, AC side is 10, and then at what how much duration, how much energy you need to store in the battery, that you need to define. The first thing, let's say 12 megawatt is on the ground, and how much they are okay to export, or every single unit generated from the solar will going to store in the battery. What is the scenario?
I don't know.
I don't know. Then please clarify on it, because see, let's say you are connecting 12 megawatt to the grid, or there is no grid available on the particular land. Does you are going to tap your power to the grid?
Inside the grid connected?
Yes. I believe yes.
Right? So yes, it's a public connections, correct? So if you're tapping to the grid, then it's a 10 megawatt AC. So in the entire daytime generation, you are pushing to the grid, correct?
Yes.
So there is technically there is no need of your Bess. But if they are willing to go for the Bess, then you should ask them for how much of percentage of energy every day you want to store in the battery, and for what purpose, and for what time you are going to use it. Like in the night time, for if you look at the operation profile, 5 to 10 p.m. if I consider, right, 5 to 10 p.m. you might be required to get the discharge of that energy, correct? But point is, on the AC side, the load would be only, you can serve for 4.5 megawatt, close to that. Because if you operate for 5 hours, right, and load of, let's say, 5 megawatt, how much energy you are going to release? 5 megawatt into 5 hours, 25 megawatt hour, correct?
Okay.
So 25,000 kilowatt hour of storage you require. So 25 megawatt hour storage you needed only. And for generating 25 megawatt hour, let's say DC side 12 megawatt, how much would be the your generation then for a day? One day, considering 4.5 unit or the 5 units. For 1 megawatt plant, it's a 5,000 units per day. Correct? 5,000 units. For a 10 megawatt plant, it's a 50,000 units. And you do require 25,000 units every day. So it means you are putting 12 megawatt hour power plants, you are putting 25 megawatt hour battery on the field, only 25, okay? Not a single day autonomy left in that. And you are going to put let's say 25, here is the 10, and yeah, your DC is fixed 12 megawatt because based upon the land availability, and maximum you do require the storage capacity of 25 megawatt hour. That's the thing.
Okay.
Are you getting this, or you have some doubt? See, I'll explain you over here. I got your scenario. See, the point is your land is available, correct? And your land is available. Within that, this DC is only 12 megawatt,
Okay.
correct?
Mhm.
And you are having a time span of 5 hours to operate with the Bess.
Okay.
With respect to that profile, they are saying this is a peak duration, morning 9 to evening 10 p.m. is the peak duration they are wanted to perform, right?
Okay.
Now, the 12 megawatt is the plant. On the daytime, if you put every generated unit to the grid, then no need of the Bess. This is not needed. The first thing. Second scenario, if they wish to go for the charging of this, okay, then partial energy would be released to the grid and 50% of energy would be used to get this device charged, get the battery charged. And the charged energy will going to use in the evening time to power your load, like
Okay.
this grid again,
Mhm.
correct? So your
Yes.
usable capacity, if you are going with the Bess, you are just managing the time and you are reducing your power, the output power. If you use your 10, like AC side, 5 will be go out in the day and 5 will be stored in the battery, and the same 5 will be used in the night time. Because your capacity is only 10 to get it generated based upon your land availability, correct?
Yes.
That's the fundamental point at your end.
Okay.
And in our scenario, we have no limitations of the land. We have, let's say, ample amount of land is available, and I need to meet my power ratings. That's the scenario.
Mhm.
Okay.
Okay, got it.
Got it?
Mhm.
So further to move
Okay.
ahead,
Is there availability that if we needed further questions in the upcoming time to ask you through the Zoom meeting, or we can or how can we communicate?
So you can put up your queries on a mail, no worries at all. Okay. Here right now you drop your email addresses in the chat. Okay.
Can you please
And
also come send us your email address?
so what I'm doing, okay, just what I'm doing, you just drop your emails. I am going to share this presentation with you. Okay. You can refer this, and definitely once I shared this presentation, definitely you will be receiving my mail.
Yes.
So
Okay.
you are having my email address to communicate later on also.
Perfect. Okay.
I have a request, if it is possible. I would like that we are going to revise the training, the course, and if it is possible to have another session to ask you if there is any more questions, and that this will be the last session. If that possible to you, if it is not, it's okay.
A Q&A session for the whole global
For the whole course. It will not be the next week. It will be we will send you an invitation about this session if this is possible to you.
What we can do, the best part, you can put up your queries right now if you are available with. We will discuss, we will extend this.
Right now there is no question, but what I'm saying that we are going to revise the entire course and the entire training, and I believe if it is better to have one last session that we are going to ask these questions to you directly, if that is possible.
See, possibly, I need to connect on weekends only. That's the part.
Okay. We can settle down and agree on a date and time.
So one thing we can do, so there are two approaches, obviously, no worries at all. If you are having a doubts, you can put me on a mail. That's the one thing. Secondly, if you wish to have one session, we will do it. No worries at all. Okay, not an issue. We will do it. One more
Okay.
session, but you can come up with the questions. For today, I kept the session itself with the case study as well as the question answers part. So I'm open right now also. If you are having any questions, you can drop now. Drop your questions. If you don't have, you are requiring one more session, but that is an additional, exactly, correct?
No, for right now, we it's all good.
It's all good. Fine. So with this, I will going to share with the PPT and some additional inputs like shutdown procedures of the plant and that few documentation. I think this page I have shared earlier also, right? So this will be going to share with you and the solution providers, the name of the solution providers too, the renowned solution providers in the market.
Okay.
And we will, conclude this entire journey. We will have one more session if you wish to.
Yes.
But that would be possibly on the next weekend itself, not middle of any time. Actually, I'll be in some other stuff, so not able to manage that.
It's okay. We can agree on that later on. Once we collect our questions and send it to you, we can accordingly agree on a date and time for that session.
Sir, please do share all the PDFs and presentations that you have referred.
Yes, Satyajit, I am going to share. Please, I request everyone to drop your email addresses in the chat, right? So I will share everything on the same email.
Oh, sure, sir, sure.
All right.
Okay.
Okay, then see you officially. I'll declare this, the entire journey is concluded. Okay. There will be like I said, the additional session as per your request. And
Okay.
we will define the timelines for the same.
Okay, thank you so much.
Yeah, thank you. Have a great day and enjoy the further challenges in the Bess. Okay.
Thank you. You too. Thank you.
Have a
Thank
good day,
you.
guys.
Have
Thanks
a
for
good
your
day.
time.
Yeah.
Nice to meet you. Bye.